Oops. All right. Good afternoon, everyone. Let's start. So today, we're going to first talk about some basic concepts in information theory. I do believe that most of those concepts you haven't heard before, so that will be a quick review, but maybe adding a little bit more in-depth content. And then we'll talk about uniformity priors and exchangeability. Okay. So the information theory and their results are very, very important in machine learning and especially in probabilistic learning, because the coding theory has a natural connection to probability. Because in electrical engineering or information theory, they always want to code some random things into binary codes, right? And they want to use the smallest cost, right? They call it like smallest channel, whatever, to get the optimal coding, right? So, but in our discipline, we mainly leverage those concepts from coding theory to measure, different random variables and the distance or difference between different distributions. These are really important. Okay, so let us first consider discrete random variables. Right? So suppose you got some discrete random variables. The random variables can be taken 1, 2, 3, 4 to k, right? But they are not deterministic in that, okay, we'll measure it at this time, it might be 3. Next minute, it might be 2. It has some randomness on the outcome, right? So a natural question in information theory is that how do we come out a measurement which can represent the information contained in the random variables? Right? So here, we usually will, the more uncertain the random variables value, the more information it contains. On the other hand, if this random variable is a special type of random variable, meaning that it is kind of deterministic, I know the random variable will always be 1. Then, because we do not have any uncertainty about the value, so the information contained in that deterministic random variable is simply 0. So this is a little bit, maybe it's a little bit counterintuitive from your common sense. Like usually people will, okay, I got a random variable. If I'm more sure about the value, I feel okay, I know more about that random variable. But in the coding theory and in information theory, things are kind of like on the contrary. The more the random variable, the more random the random variables outcome, the more we are uncertain about that. That means that we need to know more about the value it can take. So that's why we view those kind of random variables are containing more knowledge, information. So now let us assume we got such kind of measurement, right? This measurement can tell, given random variable x, how much information it contains, right? Let us assume we are Shannon, right? Who is the father of the information theory, right? When Shannon defines such a measurement, right? What kind of basic properties should such information measurement satisfy, right? So the first property should that, okay, to be intuitive, we request that our measurement of information is not negative. It's very natural, right? If you don't, if X doesn't contain any useful information, the measurement is simply zero, right? The more information it contains, the larger this measurement function. Okay? So, and the second property, natural property we can think of is that suppose you got two random variables, X, Y. Okay? If they are independent, meaning that they're not related to each other at all, then their information, their drawn information, should be the summation of their individual information. Right? This is a another natural property it should satisfy. Right? Of course, if X, Y are dependent, meaning that okay, when you know X, it implies that you know a little bit information from Y, then you shouldn't have your joint information to be the summation of the individual information, right? But if X and Y are totally unrelated, meaning that they're totally independent to each other, then their total information should be the summation of their individual information. So, given these two properties, right? Non-negativity and additivity for the independent random variables, a natural observation is we can associate this H with the probability. Okay? Because X and Y are random variables, of course, to characterize these properties random variables, we can naturally consider probability. Right? So we know that if X, Y are independent, then their joint probability is actually the product of their marginal probabilities, right? So we can see that there seems some kind of correspondence between the two, right? If you just take a logarithm over that and take negative, you define your measurement H as a negative logarithm of the probability, you got satisfy all these two properties. So first, this probability is between 0 and 1. You take logarithm, it is negative. Right? You take negative logarithm, it is positive, non-negative at least. And secondly, if X, Y are independent, you can verify that H of XY as defined here will be exactly H of X plus H of Y. Right? So that's kind of how this information measurement was invented. Okay? But next thing we need to consider is that, okay, this is just a measurement for a particular value of X, right? X is actually a random variable. That means it can take multiple different values. The chance of X taking different values can vary, right? So to get a more rigorous or natural definition of information measurement, you can define your final information measurement, which we denoted by big H, as an average amount of information contains in different values of X. Of course, we need to weight each different value with their probability. Okay? So we call this big H as state entropy. Okay? So, and in a coding theory, this is a measurement which tells us the average amount of information need to transmit a random variable X. Yeah, I believe everyone has heard of this definition before, right? The entropy. How many of you have never heard of this? Oh, really? Okay. But is this a natural definition for you? Yeah. Okay. Yeah, just to give you a sense how Shannon invented this entropy, right? Just it first connects to the probability density, and then he wants he wants this information measurement to satisfy some natural properties. And then he came out this definition. And in coding theory, if I'm taking any courses, information theory related course in ECE, you might have seen that how to come to compute the entropy, right? So suppose your X can take 8 values, and the chance of X taking each value can vary, right? This is their probability density. This is the probabilities, right? If you calculate entropy, you just do the weighted summation of logarithm of each probability. You get that the entropy of random variable X, as defined here, is 2, meaning that on average, you need to use 2 bits to transmit the information contained in X. So as we just mentioned, right, entropy reflects the uncertainty, right? You can view like uncertainty and the information as 2 sides of one coin, right? They are kind of equivalent. The larger the uncertainty of a random variable, the more information it contains, right? So we can see this point by looking at these 2 examples, right? So each of the examples just showing, okay, for some random variable, I just sample its values, right? Sample it multiple times, I draw a histogram, right? From the histogram, we can see the probability distributions of those random variables. So we can see that the first random variable from their samples, we can see that their probability distributions are more concentrated, right? It has a much more chance to take the value here, right? And much less chance to take value away from the mean, right? That means, so by contrast, you can take a look at the second random variable. You can see that, okay, although it also has the largest chance to take the value in the middle, but it also has quite a large chance to take value far away from the middle. So obviously, the first random variable's probability distribution is much more concentrated than second, right? And then correspondingly, the random variable, its value is much more certain in the first case than in the second case. And this can be verified by looking at their entropy. So you can see the entropy for the first random variable is smaller than the second. So now, we got an interesting question, right? Just consider discrete random variable, right? Discrete random variable in general, suppose it can take m possible status, meaning it can take 1, 2, 3, 4 to m, right? Then we're curious to know which distribution can give this random variable maximum entropy. What? Yes, exactly, right? But we need to show that, right? If you show that, right? Because according to the definition, entropy is simply the summation of a logarithm of each probability weighted by the probability itself, right? Because this is a discrete random variable, we require that the summation of all the probabilities, of course, the possible values be 1. So we need to introduce some Lagrange multiplier, right? Then we maximize this entropy. We can solve that. The probability that X at optimum, the probability that X takes any value should be the same, which is 1 over m. That means if you can take uniform distribution, then it can assign this random variable maximum entropy, meaning that that random variable will contain most information. Okay? Most information.
You know more about the random variable. Why do you have to do the calculation?
No, I mean, it contains most information means that you know least about random variable. This is something a little bit counterintuitive. So the more uncertain you are about the random variable, the more information it contains. The more information you know, the more knowledge you know about random variable. Like if it is random variable, take the extreme case, you know, it can only take one value. So actually, there's no uncertainty about a random variable. Then the entropy is the smallest, meaning that it contains no information.
So you have a uniform distribution, you have no idea.
You have no idea, right? It can take any value, any value through 1 to m with equal chance, right? You're most uncertain about that random variable. So that means it achieves the maximum entropy. It contains most information. Any other question? Okay, great. So now we want to extend the case from the discrete random variable to continuous random variable, right? And the natural question would be, can we define an entropy in the same way as the discrete random variables? The answer is no. You see that actually, if we follow the exact same definition as we did in the discrete random variables, your entropy will be infinite. In other words, the commonly used entropy is not the true entropy, which we usually call it differential entropy. Okay, how can we see this? Right. So the first step is very similar to the discrete random variable. Because entropy is naturally defined on discrete random variables, right? How about continuous random variables, right? We can first try to discretize our continuous random variables. Right? Suppose this is a probability density for a random variables, right? So you can see the x can take any value in this real axis line, right? So we can divide x into small beans, right? And with the length delta. So according to the mean value theorem, we know that the integral across each bean, right? The integral over each bean, right? From I delta times to I plus 1 delta. Right? This is just an integral for a particular bean, right? And the density across this bean is actually the probability mass over this small bean, right? So according to mean value theory, we know that it is equal to some point inside this bean is density times delta. Okay? So this is just the basic calculus results. Don't feel uncomfortable. This is from a calculus book, right? So we can define a rough version of the continuous random variable first, based on these beans. Right? How can we do that? Right? We can define the entropy on the discretized probability in this way. So the H, in terms of this bean size delta, is defined as the summation over all possible beans, right? And the probability for each bean is this guy, right? Pxi delta. Remember, xi is some random variable value in between this bean, right? And then take a logarithm of p of xi times delta. This is like I kind of discretize this continuous x into into a discrete random variables, which can take 1, 2, 3, 4, 5, 6, right? And the probability that this discretized random variable takes value k is actually the probability mass of the original x on this bean. Right? Does it make sense? So naturally, just like what we define integral or Riemann integral, right? We can take the size of bean to be 0. To go to the limit of 0, we expect that we can have a continuous version of entropy. Right? It's very similar to what we have learned about the definition of Riemann integral. Right? But there's a problem here. You can see that the probability is p of xi times this length of the bean size, which is p of xi times delta, right? And inside this logarithm is also p of xi times delta, right? So if you just move this delta outside, you got this guy. It's summation over p of xi times size of the being times logarithm p of xi and subtracted by logarithm delta. The reason is that because the log delta, when you take out, you have a summation p of xi in front of it, and this summation is simply 1. Right? So you got this term. So then, if we consider take delta to 0, then this guy diverges, right? Log 0 is negative infinity, right? In other words, negative logarithm delta will go to infinity. So obviously, if you just straightforwardly extend the definition for discrete random variables, it won't work, because for any continuous random variable, it will give you entropy to be infinity. So to sidestep it, we just throw it out. Let's just throw this out, right? We just preserve this summation term. And then we take the size of a being to 0, say what is the limit. Unfortunately, for this case, if you take the limit that delta goes to 0, it is actually an integral, right? So if you take delta goes to 0, you can imagine your being size. Sorry. This is your being size, right? This delta. If your delta goes to 0, we know that this probability now becomes the density at x, right? Because the delta goes to 0, and the starting point and ending point will overlap. And p of xi will becomes p of x. Right? So now it becomes an integral. So this looks normal for many, many continuous probability densities. So we define our entropy in this way, which is called differential entropy. So the differential entropy is actually different from the entropy defined in the discrete random variables, because we threw out an infinity term. Mm-hmm.
From discrete to continuous.
Mm-hmm. This one?
You can see entropy of x as expectation of minus your logarithm of t.
Mm-hmm.
Okay?
Mm-hmm.
So in this point of view, there is no difference because we have expectation of some random variable.
Mm-hmm.
You can extend it to continuous.
Mm-hmm.
We have the same result.
You think this way is because you will like, if I extend the summation to integral, it's very natural. It's not very natural, because
and we can rewrite it as expectation of minus logarithm.
yeah, expectation is on the probability mass here, right? But when you extend to the expectation for continuous random variable, then you take integral with respect to the probability density. There's a difference here. Although they look the same, because we use p of x to denote the probability that each discrete random variable take different values. We also use px to define the probability density. Right? Although their expectation is kind of like similar form, but the calculation itself is different. One is integral, one is the summation. Well, in many cases, we can just will expectation, summation and integrals kind of exchangeable, right? But in some subtle cases, it doesn't. That's why I want to specify how we get to this differential entropy. Although, okay, you can overall you can view like, okay, they have the same form in that they all take the expectation over logarithm of the density. But one is take expectation of logarithm probability, one is take expectation of logarithm of density. They're still different. And they're, in the information theoretical level, they have some fundamental difference. That's something I want to highlight. But from an upper level, well, you can just briefly view, okay, there are kind of some expectation. Any other questions regarding how we get to this differential entropy? What? Why do we remove the infinity part? If you don't remove the infinity part, if you take delta, the beam length goes to 0. This guy will always be infinity. Right? Remember, we want to. Why do we define entropy? We want to measure the different information, right? We want to measure the difference of the random variables in terms of the information amount it contains, right? If all the random variables, all the continuous random variables give you the same amount of information which are infinity, what's the meaning of defining entropy?
It looks like to me that entropy is very similar to the variance, because the variance also comes as common certain random variable. So what's the advantage of having the
yeah, variance in some sense kind of align with the entropy, but it is not always equal. For example, for some random variable, you didn't have a valid variance. If you could recall with what you had discussed for student T distribution, and if you have a valid variance, you have to ensure your degree of freedom is bigger than something. Sometimes you even cannot compute the variance. And sometimes even the variance is not sufficient to reflect how much information it contains. Variance is just telling you that how far away on average it can deviate from the mean, right? Of course, there's some kind of natural intuition that, okay, the larger it on average can be distant from the mean, maybe the larger the information contains, but it's not always that case. Although in a Gaussian distribution, this is the same, exact same correspondence, because you will see that for the Gaussian distribution, the entropy is simply the log determinant of the covariance matrix. Yes, it is. Right? But for other distribution, it's not exactly the same. Yeah. This, in most cases, it's just the same as our intuition. That's why it is very often used, right? The most often used measurement of the information it contains. Entropy is not the only way to define the information that one random variable can contain. You can define your own ways, as long as you can convince your colleagues, your other researchers to use your notions. But so far, entropy obviously is the most popular definition. So the term that is thrown out, although which is infinity, it does not mean it's useless. It actually reflects that to specify a continuous variable very precisely, it requires many, many bits. This is from the information from coding theory, right? If you want to create code, right? If you want to transmit some continuous signals, right? In the modern electrical system, people always use digit system, right? You're gonna first discretize, right? People know that the more accurately recover the signal, you have to give a denser discretization, right? If you do a rough discretization, you know you're going to lose a lot of information. Actually, this term tells you that, remember, when we derive this, we are doing discretization, right? You're imagining you kind of like discretize your continuous random variable into 1, 2, 3, 4, 5, 6, 7, right? According to the bins, right? Of course, the smaller the delta, the length of the bin, the more accurately you can represent or recover the original signal. And in the extreme, you want to completely recover the original signal, you have to make the bin length to be 0, right? Then, but that will give you infinity. That means you're gonna have you use infinite number of bits to code this continuous signal. Right? Otherwise, you always lose some information. Right? Just give you a sense about from the coding theory perspective. And another thing should be pay attention is that because in the derivation of differential entropy, we just drop some term. So differential entropy can be negative. So don't be surprised for continuous random variable, when you compute differential entropy, you get some negative value because you're not guaranteed that. So you can see that this P of X, right? This P of X is no longer guaranteed to be less than 1, right? This is probability density, right? If you have a very a very concentrated Gaussian, right? You know that this is density, right? You know that surrounding the mean, the density can be very large, can be far bigger than 1. So the logarithm of that can be positive. So don't be surprised when you calculate differential entropy for a continuous random variable, it gives you a negative value. Okay. Again, given a continuous random variable x, right, with particular mean and the variance sigma squared, right, we're curious to know which distribution will give this random variable x the largest entropy. Anyone give me a guess? What? Gaussian. Yeah, you're right. It's Gaussian. This Gaussian distribution is really kind of amazing distribution, right? If you have taken statistics class before, you must have learned the law of central limit theory, a law of large numbers, right? Whatever distribution, no matter it's discrete and continuous, right? When you take the average, right? We'll take the average of that IID random variables when the number of samples you take average goes to infinity, it always asymptotically converges to a Gaussian, right? This is very, very amazing distribution. So how can we derive this, right? So we just add few restrictions, right? We want that, of course, the integral of this density must be 1, the mean must be mu, and the variance must be sigma squared. And then you maximize the differential entropy with the 3 constraints. Of course, you need to incorporate some Lagrange multipliers. You solve that optimization problem, it will give you the optimal P of X is a Gaussian distribution. Okay. Based on the entropy, we can define conditional entropy. So conditional entropy, conceptually, it tells us, given a random variable x, how much information is left for y.
What is it so special about the
Well, I mean, intuition is a Gaussian distribution is only determined by mean and variance. It leverages the least conditions given, which is given to you. It does not append more requirements. So it contains a maximum entropy, right? Imagine that, okay, I got another distribution with mean mu and covariance sigma squared, I have an additional requirement. Then you're gonna know more about that distribution, right? So their entropy will decrease. But for Gaussian distribution, it's so simple. It's just you know a Gaussian distribution. You only need to know the mu and the sigma squared. You don't need to know any other things. So that gives you the maximum entropy. But if you want to solve that, this is not required. This is not required. If you solve that, the most convenient way will take the functional gradient with respect to p of x, which we're not gonna discuss in our class.
So it seems like there is some equivalence between like the uniform distribution for discrete variables and for the, I mean, in the sense that uniform maximizes the entropy for discrete variables. Gaussian maximizes the differential entropy for. I mean, do you see that sort of equivalence anywhere else in machine learning, in problems in machine learning?
I wouldn't say they are equivalent.
I mean, yeah, I mean, they're not equivalent.
Yeah.
I'm just saying, I mean, are there any other sort of cases in machine learning where you see this kind of similarity between the two?
Well, if you talk about similarity, that's still very different. Like for uniform distribution, it has continuous version as well. Yeah. But you have to restrict your random variable values to be bounding, right? Otherwise, you won't have a uniform distribution. And the result just tells you, okay, for discrete random variable, and if you set the chance the value the random variable takes each value to be equal, it gives you a maximum entropy. But for continuous random variable, if you specify mean and variance, it is Gaussian distribution who give you the maximum entropy rather than the uniform distribution. Okay, let us look at the conditional entropy, right? So the conditional entropy conceptually, you can understand as, okay, given some random variable x, how much information is left for y, right? So a best way to understand that is just use this diagram, right? So this is x, this is y, right? So the conditional entropy of y given x is which part? Yeah, the right part, right? Right, this part, right? And this part, the overlapping part, is usually called mutual information, right? The information shared by the two random variables, right? So the definition is here. So it is the same as the definition of entropy, except that in the logarithm, we're going to put conditional probability density rather than the joint density, right? If you put it as a joint density here, there will be the joint entropy of x and y, okay? And from the figure, it will be the area which cover the union of x and y. And it's very straightforward to show that the joint entropy is the marginal entropy plus a conditional entropy, right? I will leave it as an exercise for you guys. And the second concept, which is very important, is called Kullback label convergence, divergence, right? If you're doing Bayesian probabilistic learning, you see it for 1 million times, right? It's always talking about how to minimize the KL divergence between two distributions. Right? So the KL divergence is defined as you can view as a difference, difference, or very roughly speaking, the distance between two distributions. So I got two distributions, P and Q, right? So the KL divergence can be very roughly viewed as the distance between two distributions, although rigorously speaking, it's not distance because it doesn't satisfy symmetry. So it's defined as this guy subtracted by this guy. So I would use this one, right? So it's the integral of P of x times logarithm Q over Px, and take minus sign in front of it. And sometimes you can memorize in this way. You can get rid of this minus sign. Then you got P logarithm P over Q and dx, right? So P is the left distribution here. So from the definition, you can see that the Carroll divergence is not symmetric. If you do Q and P, now you have to switch Q and P. Most cases are different, right? This interval is different, right? So from the coding theory, I just want to give you a sense. Carroll divergence tells us if you want to use distribution Q to transmit information for P, how much extra information do we need? Okay. But what we need to know is that Carroll divergence is a measurement of difference between two distributions. Carroll divergence is widely used to measure the difference between two distributions, and you can show that the Carroll divergence is always non-negative. And it is zero if and only if the two distributions are the same. And again, to show this, you can directly apply the Jensen's inequality. Right? So again, I will leave it as an exercise for you guys. And another important point for the Carroll divergence is that they're usually asymmetric, asymmetric. So Carroll divergence plays the key role in approximate inference. We'll talk about it again in our following lectures. And all the deterministic approximate methods like variational inference, like message passing, aims to minimize the Carroll divergence between the true posterior and the approximate posterior, or in the reverse direction. So basically, I can give you a sense how currently people are doing approximate Bayesian inference because the true posterior is so hard to compute. I don't know the form. So I'm gonna pre-assume a family of distributions. So this is a ground truth, right? This is my family. I want to pick up a best one in my family, which is closest to the ground truth. But how do we measure the difference between my approximate distribution and true posterior Carroll divergence? Right? There are also other, there are alternatives to Carroll divergence, but it's far less popular. So in general, we can have alpha divergence, which can be viewed as a more general version of Carroll divergence. Right? We'll discuss about this later in detail, right? Oops. Okay, mutual information, right? As we just mentioned. Mutual information conceptually, you can view it as the measurement of amount of information two random variables share, right? So this is a definition. So the mutual information is defined as Carroll divergence from the joint distribution and the product of their marginal distributions. Right? So if you calculate, if you want to calculate, you just calculate the integral p of xy logarithm px times py over pxy dx dy. Right? So there is one well-known result, and which is the mutual information equals to the marginal entropy subtracted by conditional entropy. Right? So this result can be easily seen in this way, right? So because mutual information is the information shared by two random variables, right? So it is this overlapping part. Right? So this overlapping part, the area of the overlapping part can be either computed by subtracting the marginal entropy of this guy by the conditional entropy, right? Conditional entropy will be this guy, right? Or the marginal entropy of this guy subtracted by the conditional entropy another side, right? Again, I suggest you to try to prove this. It's quite straightforward. Right? Okay, so those are all the necessary knowledge we should know about information theory, right? So you need to know what's the definition of entropy, right? How is differential entropy is derived, although it kind of like have kind of unified form as compared with the discrete case, right? But underlying concept is different, right? And entropy is an indicator for uncertainty. And what's the definition of KL divergence and properties? Especially it is asymmetric, right? And also what's the definition of the neutral information? Okay, any question regarding those definition of the basic concepts? Great. Oops. Okay. Now let us talk about. Yeah. These in philosophy, non-informative parts and exchangeability, right? This should be the another piece of the final piece of fundamental knowledge we want to discuss, and then later we'll proceed with some Bayesian models and algorithms, those kind of things, right? So we're gonna first talk about what is the philosophical difference between the Bayesian guys and the frequentist guys, right? Those two groups of people are kind of debating for centuries. So right now, at the beginning, like the frequentist guy is kind of dominant, right? Bayesian are really a small group of people struggling. Right now, things looks like kind of reversed. I'll explain it later. And then we'll talk about uninformative parts and why it is called uninformative parts and what is the idea of objective Bayesian. And then we'll talk a very important concept called exchangeability and definite theory, right? You see that exchangeability actually plays the central role of Bayesian modeling, and actually gives you some justification why Bayesian philosophy is good and is right. Okay, first I want to highlight the difference between the Bayesian viewpoint and frequentist viewpoint. So we can consider our task is to estimate some parameter theta, right, from a set of observations x1 to xn, like again using the core tossing experiments as an example, right? So I throw the coin, I want to see the head up or tail up, right? So we know that there is a parameter theta tells me the chance you have a head up, right? But I don't know that. I don't know the actual value, but we know that this experiment outcome is controlled by this parameter. So I want to estimate this parameter theta, which is central probability, right? How can we do that? The frequentist guy will just toss this coin for 100 times, right? And count how many heads up, how many tails up, and calculate the ratio. Right? It's a very natural, intuitive way. And what is the intuition, or what is the principle underlying this way of doing it, of estimation? Right? In the frequentist point of view, theta is some kind of unknown yet fixed parameter. Like you know, it is a constant unknown parameter is there, right? My goal is that through many experiments, I want to get closer and closer to this ground truth. There is not any randomness on this theta. The theta is there. It might be in the sky, might be in whatever place. I don't know. But I know, okay, it is existent. I just don't know it. So I want to use all kinds of experiments. I want to do many experiments so that I can get my estimation to be closer and closer to the ground truth theta. That is how frequentist people view the model parameters. For example, using MLE, right? We want to estimate it from the observations. We want to take a logarithm of the log likelihood. We want to maximize the log likelihood we found estimate, right? And once you get such an estimate, right? The frequency point of view, okay, this is ML estimate is essentially another random variable. So the uncertainty comes from your estimate itself, not from the parameter value. So the parameter value is always fixed. Say the parameter value may be 0.7, right? I just don't know 0.7, but I don't believe 0.7 is associated with any randomness. On the contrary, the randomness is only in my estimate because I do it, I estimate by say my estimation is 0.6, right? Which comes from an average of 100 tossing experiments. But because each tossing experiment is also random, so my estimate itself is also random. So if I want to consider the uncertainty, it just characterizes the uncertainty in my estimate. It is a random variable. And then you see that all kinds of techniques like hypothesis testing, like a confidence interval, right? So the confidence interval just assumes, okay, my estimate, say the average of 100 outcomes will follow some distribution. I want to estimate the parameter of this distribution and how likely that the true parameter falls in, say, my estimate subtracted by 1 standard deviation, my estimate plus 1 standard deviation, right? So all the uncertainty is reflected in my estimate rather than the ground truth value of the parameter. Right? This is all we have learned, I mean, from our elementary course of statistics. Right? Is everyone comfortable? Right? But Bayesian takes a totally different idea. In Bayesian world, everyone is random. Not only including my observations, my experiment outcomes, but also the parameter value. So we assume there's some randomness on this parameter as well. So that means in our viewpoint, we're gonna first generate some random variable, theta, from some prior distribution. Then given this value of theta, we generate each observations. That's why when we write down the joint probability, we need to consider the prior of the parameter theta and also the likelihood given the parameter of each observation. Then our goal is to infer the posterior distribution of your parameter. It's not point anymore. And your uncertainty from estimation is reflected in this posterior distribution rather than any of your estimate. We don't have any estimate. So you can imagine at the beginning, you don't have any data, right? You don't have any data, you kind of have a very flat, very wide prior, right? Your data comes from this prior, sample from this prior. It can be anywhere, right? And then once, it's better to use some, this is some prior, right? It can be quite wide prior, right? Theta is generated from here, right? It might be here, right? Suppose it is generated from here, right? And now, given this theta is generated a bunch of observations. So now if you can compute the posterior distribution of your theta, we expect that the posterior distribution is much more concentrated. But that does not necessarily mean that it will converge to a point. You still have some uncertainty on that because you only observe like 100 times. It's not sufficient for you to do 100% sure identify the value. Right? So your uncertainty of estimate is also reflected in the distribution, which is now the posterior distribution. So this is a key difference. So in Bayesian world, everything is random variable, and everything can be random, and every variable can be viewed as a random variable. Right? So this is just a philosophical choice, and in theory, there are actually very strong connection between the frequentist point of view and the Bayesian point of view. I can give you an example. Like in frequentist point of view, right? You assume theta is a constant, unknown constant value, right? You got all kinds of estimate. And in many estimate, for example, MLE estimate, they can show that when the number of observations goes to infinity, then your MLE estimate will converge to the ground truth value in probability or in distribution. You have different types of convergence, but anyway, it just converges to that, and almost surely, right? And for Bayesian, it's very interesting. We said that, okay, suppose this is your ground truth value theta, right? You got some 100 examples. When you calculate posterior, you got a much more concentrated posterior distribution, which can help you know much more about the theta value, right? But if you got many, many observations, say the number of observations n goes to infinity, guess what will happen? Yeah, now how does it decrease down? Sorry. Yeah, I mean, yeah, don't consider that complicated. Just to give you the result. So, if you make this n goes to infinity, then this posterior distribution will now converge to a spiky distribution, meaning that you only have probability mass at this 1 point, and for the other density is simply 0. Well, I mean, more rigorous speaking, this is called delta probability or delta distribution or delta measure. Okay. This is kind of have same meaning with the frequent response view, because frequent response view think theta will be just the point, right? And when your number of observations goes to infinity, your MLE estimate, whatever other estimate, will converge to that. Okay. So for the Bayesian point of view, if you make your n goes to infinity, your posterior distribution will now converge to a point, 1 point distribution, which is just the delta measure. Because you will not have any uncertainty about theta, right? If you have enough data. Okay, any question? Mm-hmm. Yes, prior distribution. So prior distribution usually is kind of wide and flat, right? And the posterior is much more concentrated, right? Because you can use your information, your data information to better locate where theta might be. So, and then the question would be, okay, why should we believe the parameter value of theta is random, right? Or what's the benefit of making such kind of modeling choice? Right? You got frequently point view, like you will theta has no randomness at all. You just want to estimate theta through the experiments. Or you choose Bayesian point of view, you believe, okay, theta is just random, right? And I should assign some prior with that, right? Why we should prefer Bayesian point of view? Right? So the first benefit is that we can encode our beliefs, previous experience, and desires in the prior of P of theta. This is actually quite important, especially in artificial intelligence, as we actually discussed about that point in our very first lecture, right? So we know that in artificial intelligence, machine learning, human learning is always like lifelong learning, right? Before you learn something, you always have some prior knowledge, preferences, or induct bias about that thing, right? And after you absorb new information, you kind of like integrate the information. You change your beliefs about theta. So if you choose Bayesian framework, it's very natural to model such kind of learning framework, right? You can use prior of theta to represent your prior beliefs, previous experience. And then after you absorb information, you compute the posterior distribution, right? To represent your updated beliefs. That's why Bayesian formulation is very popular in the machine learning area. A second thing is that we can make probabilistic statements about theta, right? Because we model theta as a random variable, and our goal is to compute the posterior distribution of theta. Then we can get all kinds of statements about theta, like mean, variance, quantiles, whatever things you want, right? But if you use frequentist point of view, well, because theta is just the point, right? The things you can get is just some estimate about theta. And the problem is that you can not see too much about theta, right? You can only see something about theta hat. This is kind of very, very inconvenient. And plus, in the frequentist point of view, they always assume, okay, my experiments can do 1 million times, right? I can do as many as I want. As long as I have enough number of experiments, I can make a better guess to the ground truth. But in many real-world applications, you are not allowed to do 1 million experiments. Right? Some experiments you can only do once or twice. And in that case, you still want to infer after doing that kind of experiments, what is my belief about quantity of interest, right? Of course, in that case, Bayesian formulation is more attractive. And the third thing is about the prediction. I just give you some idea because you will see the benefit later when we touch the specific problems. Right? But the benefit is that we can make Bayesian prediction that integrates all possible outcomes. Right? That will make your prediction more robust. So because of the prior beliefs or prior knowledge that can be encoded as a prior distribution, many people or researchers view Bayesian analysis is kind of subjective, right? Because you're kind of mixing or mingle your subjective beliefs and the data in practice, and you mix them together, you get updated beliefs, right? So many people will like Bayesian analysis of subjective, right? But it's actually not necessary. Bayesian indeed provides a convenient way to incorporate subjective beliefs, right? Which is important for AI, but it can also use uninformative priors, which we're going to discuss right now, right? If we use uninformative prior, this is called objective Bayesian. Right? So this point is often criticized by the frequentist because frequentist always says, okay, you're not doing objective things. We're doing science. Science should be objective. You shouldn't incorporate any subjective beliefs. But actually, frequentist or frequentist models also make assumptions as well, right? If you do any hypothesis testing or confidence interval estimate, you have to make some assumption about your estimate, right? In many cases, you're assuming your MLE estimate or whatever estimate follows some Gaussian distribution or follow some student t distribution. Without this distribution form, you can't get some interval estimate, right? This is also a very strong assumption. But whatever, although I'm kind of personally in favor of Bayesian point of view, I'm not, but I'm also open to frequentist view. Whichever, whether you use frequent Bayesian models, please always check the assumptions you make. Okay, so these are about the idea of the Bayesian word and the frequentist word and their key difference. So now let us talk about uninformative parts. Right? So as we just mentioned, right? So Bayesian in a Bayesian formulation, Bayesian modeling, we are flexible enough to model everything as a random variable. And for any random variable, we can assign a prior, which can encode our prior beliefs, bias, whatever. Right? So of course, such kind of flexible formulation incurs criticisms, right? So what if I want to make my estimation more objective? In that sense, I don't want my posterior distribution to be largely influenced from the prior. Then what kind of prior should we use, right, to ensure that the posterior distribution is mostly determined by the data rather than the prior? So such kind of prior is called uniformity prior, right? As the name suggested, right? So objective Bayesian, which is just a sub-discipline in Bayesian research, prefer the priors to have a later influence on the posterior distributions. Such a prior is called uniformity prior. In other words, they want to maximize the effect of the data. In other words, they want to let the data speak for themselves. They want our prior to import as little information as possible. So now I want to ask, if you want to assign such an uniformity prior, which prior do you have immediately in your mind? Yeah, uniform, right? A very intuitive choice of an uniformity prior is the uniform distribution, right? It reflects our intuition that since I do not know which parameter is more likely to be sampled, right? Let's just assume the chances are always equal, right? It can take this value, can take that value, it can take a third value. All they have exactly the same chance to take the same value, right? If you have a discrete distribution where you have a finite number of states, the uniform distribution, suppose you have a k possible values, k categories, right? Your uniform distribution is just 1 over k, right? And if you have a finite interval and your random variable is continuous, then your uniform distribution is actually density, right? Is 1 over the length of the interval. Right? But in both cases, you're assuming the range of your random variable is bounded, right? What if your random variable has unbounded domain? Like, for example, I just assume my random variable is continuous, right? It can take any value across in the real space, right? In that case, we actually don't have a valid uniform distribution. But from a pragmatic viewpoint, we just define our uninformative uniform distribution to be proportional to some constant. This is not a valid distribution. This is just for pragmatic reason. Why? Because if you assume this P of lambda is proportional to constant, of course, you want to normalize it, right? You want integral to be 1, and if you do this integral, it's just diverges, it goes to infinity, right? But we still use it. And as long as if you plug this into your posterior distribution, like P of lambda, okay, times P of D given lambda, which is likelihood, right? If you plug this into the computation of posterior, if the posterior is still a reasonable posterior, is a valid posterior, then we can still use it. And this is called an improper prior. So now comes the question, right? Is uniform distribution the best uninformative prior? Or we should use uniform distribution and it's an improper version for unbounded domain as our ultimate choice for the uninformative prior? The answer is no, because uniform distribution has the problem, right? The problem is that they are not translation invariant. So what does it mean for translation invariance, right? So suppose you define such a uniform distribution or uniform prior for lambda, right, which is proportional to constant, right? So now if I make some kind of transformation over lambda, say I define lambda equals to eta squared, right? So now if I want to look at the prior over eta, will the prior of eta uninformative as well? It's actually not. We can verify this, right? We know lambda itself is uniform, although it's improper. We know, okay, P of lambda is uninformative. Now we just made some transformation, right? We know that we can represent eta in terms of lambda, right? So now, and the lambda is eta squared, right? So if we look at the prior of eta by applying the formula we talked before, right? If we do the random variable transformation, if we compute the density of the random variable, we just apply this formula, right? We can find that now the prior of eta is proportional to eta. It's not proportional to some constant, fixed constant. That means the prior of eta, which is the transformation of lambda, is no longer uninformative. So this tells us, although uniform distribution is kind of like a nice choice of uninformative prior, it does not mean it's perfect. It also has some deficiency. Okay. So then to address such kind of deficiency, like translation invariance problem, right? We consider what kind of prior can guarantee translation invariance. Right? That means, okay, if this variable, say lambda, has some uninformative prior, right? And if I do any kind of transformation over lambda, the transform variable will also follow the same form of uninformative prior. Do we have such kind of prior distribution? I'm afraid not. Yeah, we'll talk about that. We'll talk about that. But let's consider different type of translation invariance, right? And then we're gonna look at the general uninformative prior, which satisfy the translation invariance. Right? So we can first consider one particular type of translation invariance is called a shift invariance. So what is shift invariance? If the likelihood take this form, so x is our observed random variable, and lambda is the random variable which controls this likelihood. Right? If the likelihood takes this form, right, and then our lambda is called a location parameter, and this density we conclude it x-based shift invariance. What does it mean by shift invariance? Means that actually the likelihood is only determined by the relative difference between the observation and the lambda, right? It doesn't matter which absolute location you start with, right? Means if you add both x and lambda to the same position C, their likelihood won't change. Right? So if you define x hat and the lambda hat in this way, your likelihood is the same as P of x given lambda. So now we want to construct a prior that reflects this shift invariance. Why do we want construct prior to reflect shift invariance? Because we want this prior to be more consistent with the likelihood. Why should we make the prior more consistent with likelihood? Remember, we want to our prior to has the influence on the posterior as least as possible. So the more consistent the prior's property with the likelihood's property, the less likely that they're gonna battle with each other in computing the posterior, right? And then the posterior is more dependent on the likelihood. That's the motivation. And then the problem is, how do we choose a prior, right, that satisfies the shift invariance? We can choose a prior that assigns equal probability mass to an arbitrary interval in B as to the shifted interval A plus C and B plus C. C can be arbitrary value. And in the mathematical formulation, it will be like in this way, right? For any interval A and B, right? And the probability of your prior in this A and B should be the same as you shift this interval by C, right? Let's see what kind of prior P of lambda could satisfy this shift invariance. So if you do some integral variable transformation, like you can define new variable lambda hat, lambda bar, which will represent lambda equals lambda bar plus C, and you can see that you can replace this lower bound, upper bound in the integral by A and B, right? And do some integral variable transformation. You can see that you get the same integral interval, right? And then because this equation should be the same, should hold for any choice of A and B. That means the integram must always be the same, right? So that means P of lambda is always equal to P of lambda plus C. This just tells us P of lambda won't change, right? Won't change across the domain, right? So it tells us P of lambda is actually proportional to the constant. In other words, the uniform distribution is a shift invariance. It's shift invariant. To give a concrete example, right? If you take a look at the Gaussian likelihood, right? Suppose we know its variance, right? We just don't know the mean. So from the density of the Gaussian likelihood, you can see that it is determined by the difference between x and mu, right? So actually, the the Gaussian likelihood is a shift invariant for the mean, right? It's a shift invariance density, right? And if you take a like conjugate prior over mu, right? That means I want to assign prior over mu. This prior should be conjugate to the Gaussian likelihood, right? It will be another Gaussian distribution. Right? Someone asked if it is possible that your conjugate distribution has the same form as the likelihood. Yes, it has some case, right? For example, the Gaussian mean. Okay. So by contrast, the conjugate prior, if we look at the shift invariant prior, which is a uniform distribution, an improper uniform distribution, we can see the connection between the conjugate prior and the uninformity prior. When you take the variance of the conjugate prior goes to infinity, right? Because the conjugate prior is Gaussian, right? If you take the variance goes to infinity, it now becomes a flat uniform prior. It's actually the uninformity prior. In this case, for the Gaussian mean, is the limit of the conjugate prior. Okay, let us stop here today. On next Tuesday, we'll talk about another type of translation invariance, which is called skew invariance. Then we'll proceed to the general translation invariance. So the general distribution, uniformity prior distribution, which satisfies arbitrary translation invariance, is called Jeffreys prior. We'll talk about the pros and cons of Jeffreys prior. Okay, see you on next Tuesday.